Welcome back to the deep dive. Today we are tackling, well, a pretty monumental chapter of scientific study, the comprehensive world of electrochemistry.
We really are. And our mission today is to take that entire textbook, chapter 20, and sort of distill it. We want to turn it into a flowing audio guide that connects all the dots, from the basics of redox all the way up.
Exactly. Every concept, every rule, every formula you need to know. But, before we jump into the theory, the source material had this fantastic hook I wanted to start with. It's about using electrochemistry for massive environmental cleanups.
Oh yeah, the brown field sites. It's such a powerful application. You have these industrial areas that are just saturated with toxic heavy metals, things like cadmium, copper, or even cyanide ions.
And they're stuck to the soil, right? You can't just wash them out.
No, they're locked on.
Yeah.
So what you do is you apply electrochemistry. You run a powerful electric current through the soil, which forces the water in the soil to break down into H plus and OH minus ions.
And these are much more mobile.
Way more mobile. They get in there, and they essentially knock the poisonous metallications and the cyanide anions off the soil particles. The heavy metals then migrate to the negative electrode, cyanide to the positive, and you can just collect or remove them in this circulating fluid.
It's just an incredible example of forcing a chemical reaction to solve a huge problem. And that's a perfect place to start, really, with the absolute foundation of all this redox reactions.
Right. We have to do a quick recap. Electrochemistry is all about electron transfer. So oxidation is loss of electrons. The thing that gets oxidized is the reducing agent.
And the opposite, reduction, is a gain of electrons. And that species is the oxidizing agent.
That's the vocabulary. You have to be fluent in it.
Okay, so with that in our back pocket, let's look at the first major branch, electrolysis. What exactly is it?
Electrolysis is basically the decomposition of a compound. You're splitting it back into its elements using an electric current. Industrially, it's massive. It's how we get aluminum, how we make chlorine gas, how we purify copper.
And to do this, you need an electrolytic cell. So you've got your electrolyte, which is either a molten salt or a concentrated solution,
Right.
and two electrodes hooked up to a DC power supply. Has to be direct current.
It's absolutely key. And here is the one rule, the one thing you absolutely have to internalize, whether we're talking about electrolysis or, batteries.
Okay, what is it?
Reduction always occurs at the cathode. Always.
And for electrolysis, because the power supply is forcing the reaction, the cathode is the negative electrode. It's attracting those positive cations.
Precisely. And the anode is made positive, so it attracts the negative anions, which then lose their electrons. And losing electrons is oxidation. So oxidation always happens at the anode. It's a forced redox reaction.
Which brings us to the quantitative part. How much stuff do I actually make?
Well, the math here is based on a really straightforward relationship. The mass of substance you produce is directly proportional to two things: the strength of the current and the amount of time you run it for.
And we combine that into the formula Q equals I times T.
Yep. Q is the total charge in coulombs, I is current in amps, and TIT is time in seconds. And please, don't forget to convert your time into seconds. It's such a common trip-up.
So once we have our total charge Q, we need to connect that to the number of moles. That's where the Faraday constant comes in, right?
It's the absolute linchpin of this whole topic. The Faraday constant, F, is the total charge carried by exactly 1 mole of electrons. Its value is 96,500 coulombs per mole.
So it's the bridge. It connects Avogadro's number with the charge on a single electron.
It is the bridge. And so the half equation for your reaction tells you everything. If you're trying to deposit lead from a lead 2+ ion, you need 2 electrons.
So you'll need 2 Faradays of charge to make 1 mole of lead.
Exactly. Let's run through that worked example. Say we pass a current of 1.50 amps through molten lead bromide for 20 minutes. How much lead do we get?
Okay, first things first. 20 minutes is 1,200 seconds. So step 1 is calculating the total charge, Q.
So that's Q equals 1.50 amps times 1,200 seconds, which gives us 1,800 coulombs. That's our total electrical budget.
Right. And step 2, we look at the stoichiometry. We need 2 Faradays for 1 mole of lead. 2 times 96,500 is 193,000 coulombs. And that amount deposits 1 mole, or 207 grams, of lead.
And now it's just a simple proportion. If 193,000 coulombs gives you 207 grams, then our 1,800 coulombs will give you Well, you do the math. 1,800 over 193,000 times 207.
And that works out to 1.93 grams of lead. It's such a reliable method that historically they actually use this process in reverse to help figure out the value of the Avogadro constant itself.
It is a beautifully direct link between electricity and mass. Okay, so now let's pivot. Let's go from using electricity to force a reaction to using a reaction to generate electricity. This is the world of electropotentials.
This happens when you put a metal into a solution of its own ions, like a zinc strip in zinc sulfate. You get a redox equilibrium right at the surface, which creates a voltage, an electrode potential, E.
Correct. But you can't measure it in isolation. You can only ever measure the difference in potential between two of these half cells. And the really critical convention here is that we always write the potential with respect to the reduction reaction.
So the electrons are always on the left-hand side of the equation.
Always.
And what does the value of E actually tell us?
It's a measure of pulling power, really. A more positive E value means the ions are really good at pulling in electrons. They're easy to reduce. The metal itself is unreactive.
And a more negative E value means the opposite. The ions are hard to reduce. The metal is very reactive and wants to give away its electron.
Exactly. It's a powerful reducing agent.
To measure any of these, we need a universal baseline. That's the Standard Hydrogen Electrode, the SHE.
We need it because we've all agreed to define its potential as exactly zero. By convention, the standard electrode potential, E0 of the SHE, is 0.000 volts.
Can you just describe the setup for us?
Sure. You have a platinum electrode, which is inert, but it's coated in this spongy platinum black to give it a huge surface area. It's dipped into a 1 mole per decimeter cube solution of H+ ions.
So a strong acid.
Right.
Yeah.
And you're bubbling pure hydrogen gas over it at standard pressure, 101 kilopascals, all kept at 25 degrees C. Everything you measure against that, under those same standard conditions, gives you its standard electrode potential, its E0 value.
Okay, so let's build a cell. We take two half cells, say zinc and copper, and connect them. What are the two crucial things we need to make it work?
You need your external circuit, obviously, with a high-resistance voltmeter. But just as important, you need the salt bridge.
The little piece of filter paper soaked in something like potassium nitrate, what's its job?
Its job is to complete the circuit internally. It allows ions to flow between the two beakers to balance out the charge that's building up. Without it, the reaction would stop almost instantly. It's a critical component.
Okay, so with the two half cells connected, we can calculate the voltage of the whole cell, the standard cell potential.
And the rule for that is simple and rigid. It's always E cell equals E more positive minus E less positive.
Let's use silver and zinc. Silver is plus 0.80 volts. Zinc is minus 0.76. So the cell potential would be plus 0.80 minus a negative 0.76.
Which gives you a really healthy positive 1.56 volts.
And that positive number doesn't just tell us the voltage. It tells us the direction of electron flow and which electrode is which.
It tells you everything. In a spontaneous cell of battery, the half cell with the more positive E0 is the positive pole. That's where reduction happens, is the cathode.
Hold on, that's a huge point. In electrolysis, the cathode was negative. Here, in a spontaneous cell, the cathode is positive.
That is the conceptual hurdle everyone struggles with. But it makes sense. Reduction is happening, so it's pulling electrons toward it from the external circuit, making it the positive terminal. Electrons always flow from the negative pole, the more negative E0 value, to the positive pole.
And this is how we predict feasibility, right? Can this reaction happen on its own?
Yes. The E0 values are our strength scale. The species on the left of the half equation with the more positive E0 is the stronger oxidizing agent. The species on the right of the half equation with the more negative E0 is the stronger reducing agent.
So a reaction is feasible if the best oxidizing agent reacts with the best reducing agent.
Right. And there's a neat visual trick for this. If you list your half equations with the most positive one on top, a feasible reaction will always proceed in a sort of clockwise direction.
Okay, let's try it. Will chlorine gas at plus 1.36 volts oxidize iron 2 ions at plus 0.77 volts?
Yes, absolutely. The chlorine half cell is much more positive, so chlorine gas is a much stronger oxidizing agent than A3+, and E2+ is a better reducing agent than chloride ions, so the reaction is definitely feasible.
But all of this is based on standard conditions, which rarely exist in the real world. What happens if we change the ion concentrations?
Qualitatively, you just think about Le Chatelier's principle. For an equilibrium like A3+ plus an electron gives F2+, if you increase the concentration of the stuff on the left, a Fe3+, you push the equilibrium to the right.
Which favors reduction.
Favors reduction, and that makes the electrode potential, E, more positive. If you increase the concentration of the product, the V2+, you push it back to the left, and E becomes more negative.
And there's a rule of thumb, isn't there? If the standard potentials differ by more than about 0.3 volts, the reaction will probably happen regardless.
It's a pretty safe bet, but for a proper quantitative answer, you need the Nernst equation.
Right. This is the tool for calculating the actual electrode potential, E, when concentrations are not 1 mole per decimeter cubed.
It is. And the simplified version at 298 Kelvin is E equals E standard plus 0.059 over Z times the log of the concentration of the oxidized form.
Where Z is the number of electrons transferred in the Hass equation. And this equation neatly proves the definition of standard potential, because if the concentration is 1, the log of 1 is 0, and that whole last term just disappears.
And E becomes equal to E standard.
Yeah.
Exactly. But there's one huge caveat we have to mention before we move on. E0 values predict if a reaction is feasible. They tell you nothing, absolutely nothing about the rate.
Right. The classic example is zinc reacting with cold water. Thermodynamically, it should happen. The E0 values say so. But kinetically, it's so incredibly slow, you'd say no reaction is occurring at all.
Precisely. It's a prediction of possibility, not speed.
Okay, let's use our last bit of time to circle back to electrolysis, but this time with aqueous solutions, where things get trickier.
Yeah, molten salts are easy. Only 2 ions are present. But in water, you also have H+ and OH- ions from the water itself, and they're always competing at the electrodes.
So, at the cathode, the site of reduction, how do we decide which positive ion gets discharged?
You go back to the E0 values. It's a competition. The cation with the most positive E0 gets reduced first, because it's the easiest to reduce. It has the strongest pull in the electrons.
So that's why in a solution with copper ions, hydrogen ions, and sodium ions, the copper at plus 0.34 volts will always be discharged before the others.
Always. But the anode, where oxidation happens, is more nuanced. You have to consider the E0 value, sure, but also concentration plays a huge role.
This is the exception to the rule, isn't it?
It is, especially when the E0 values of the competing anions are quite closeless than that 0.3 volt difference we mentioned.
Give us the classic example here.
Concentrated sodium chloride solution, brine. Based on standard potentials, you'd expect the hydroxide ions to be oxidized to produce oxygen gas. But in a concentrated solution, there are so many chloride ions crowded around the anode that statistically they get oxidized instead, producing chlorine gas.
So concentration can override the standard potential prediction?
It can be the deciding factor. If you make that solution very dilute, then the prediction flips back, and you get oxygen from the hydroxide ions instead. Concentration is the tiebreaker. So to pull it all together, what electrochemistry really does is give us a numerical scale, the standard electrode potential, to understand and predict redox reactions. It lets us calculate what will happen when we force a reaction with electricity, and what will happen when we harness a reaction to create it.
And as a final thought for you to take away from this, think about how those small changes in concentration, the ones described by the Nernst equation, have massive real-world consequences. A slight shift can determine whether an industrial plant produces valuable chlorine or worthless oxygen. It determines how well your electric car battery performs on a freezing cold day. Standard conditions are the theory, but the real world is always non-standard.
That's a great point to end on. Thanks for joining us for this deep dive.
And a warm thank you from the Last Minute Lecture team. We'll see you next time.